We are in 15.3. Coulomb's law.
Yeah.
It looks like a BMW to me. I can't see, like, I can see like the edge, the styling, the colors. BMW likes that stuff. So I think that's what that is. And we got an electric car. It says they're becoming more popular. Well, they were. I still think they're on the up, but not as quickly as they were. You know, talking heads on TV, I think most of them agree it's like people that wanted an electric car by now have one. And other people that want one can't afford one. So until the costs come down and the technology gets a little better, they're still kind of an oddity. I mean, the principal in the building has two, but he makes, you know, twice what the rest of us make. So that makes good sense. Energy costs for electric vehicles.
Wait, don't you have one?
Used to. Yeah, I'm actually going to talk about it here just now. Electric cars average about 1/3 the cost of gasoline cars. Energy costs. So when I did have an electric car, first of all, it was used. The only reason I had it because I got it at a really steep discount. Why? Because electric cars drop in value faster than regular cars. If you want to turn $60,000 into $20,000 in about 3 years, buy an electric car. It's a really good way to destroy value, destroy money. But yeah, my little car, I had to go 16 miles was my one-way trip to work. Okay, 16 miles one way. If I had the gasoline version of, it was a Kia Soul, those cars get about 32 miles per gallon. Okay, I'm actually telling a story right now, so you're probably not going to have eyeballs on your computer screen, so you need to stop what you're doing and follow along. Okay, 32 miles per gallon. How many gallons of gas would it take for 1 day's driving going to work and back? One, because 16 miles there, 16 miles back is 32 miles, and the car would get 32 miles per gallon. That's the gasoline version. How much does a gallon of gas cost?
About like $2.75.
Since when?
$5.
We'll just say $3. Can we say $3? We've been around $3 for the better part of the last year. Okay, so $3 a gallon. My electric car, I ran the numbers, and if I believe what the ratings say and everything, and I could actually, if I was using the trickle charger, I could put a meter on it, right? So it took 80 cents of electricity to drive to work and back. So $3 in gasoline or 80 cents in electricity. So that's the difference. So wait, isn't 80 cents kind of close to $1?
Yep.
Yeah.
And $1 is 1/3 of $3.
Yep.
So that checks out, right? 1/3. But they don't travel as far. Now they've made up the difference since then. How do they make up the difference? Are the electric cars more efficient than they were just a few years ago?
Isn't it hybrid?
No, not really. They just put bigger batteries in them. So they extend the range longer by putting bigger batteries. That'd be the same as a gasoline car. Well, this car doesn't go far enough on the tank of gas. Make the tank bigger, right? That's the same thing. What?
What about hybrid cars? How's that work?
Hybrids combine a gasoline engine with an electric battery and electric motor. So you've got a little bit of both.
Are they better?
It depends your purpose, right? So for my purpose, my electric car was awesome because I didn't have to go very far. I just used it to go to work and back. And I have a fleet of cars in my family, so if I needed something that could go further, I'd just drive a gas car. Does that make sense?
Yeah.
So whatever your purpose, you have to buy a car that fits your purpose. So anyhow, Coulomb's law. The questions regarding the relationship between electrical force, the size of the charge, and the separation between the charges were solved by Charles Coulomb in 1785. When you think of 1700s and electricity, who's the first scientist that pops into your head?
Albert
Newton.
Einstein.
Newton.
Einstein.
Electricity.
Oh, James Madison.
Wow.
Einstein.
I'm literally thinking Ben Franklin,
Oh, yeah.
I forgot about that dude.
right? And I'm thinking, man, this is 1700s. Here's the level of their understanding. I'm going to fly a kite with a string and a key. And I'm going to hold on, and I'm discovering that lightning is electricity. This is foundational work, folks. So when I think of 1700s and electricity, I thought Coulomb's law, before I read this, in my mind I'm thinking like 1800s probably. Nope. 1785. What happened just 2 years before that? American history.
Light bulb.
The American Revolutionary War. 1785. Wait, way before the light bulb, by the way. We had just won our independence from the British. This is like the age of not even rifle bored muskets. I mean, they had some, but this is pretty old. All right, so we're talking that we're still in the age where men would wear wigs, powdered wigs. This guy's thinking of things that we still use today as far as electronics, right? We're still using Coulomb's law. So here we go. Put in your notes that formula. Fe equals K Q1 Q2 divided by D squared. Oh my heavens, it's not that complicated. Take a breath. Take a second, compose yourself. The Fe. What does F usually stand for in physics? Force. E just means, okay, where is that coming from? This is electrical force. So Fe is electrical force. The K is new to us. It is a constant. K is a constant of proportionality. Okay? We don't need to know tons about that in Intro to Physics, just like we didn't need to know tons about the gravitational constant when dealing with Newton's law of gravity. We're given it. Okay? We're given it. And then Q1 and Q2 are two charges. So we've got charged particles. And then we divide by the square of the distance between those two charged particles. So you got two charged particles. Depending on how far away from each other they are, you'll have how much force, electrical force, they would exert on each other. Whether it's a repulsive force, a push, or whether it's an attractive force, a pull. Okay? And then this paragraph just repeats what we just said, but I'm going to read it anyway. In this equation, Q1 and Q2 are the two charges, D is the distance between the two charges, and K is a constant of proportionality that is given to us. Fe is electric force, which occurs as a result of interactions between the two charged particles. For the purpose of calculating, this is a disclaimer, so we're going to skip that sentence because I don't want to confuse anybody. It's a disclaimer. Basically, it's saying we're going to keep the math simple. Okay? Yes.
Oh, your mark's up there.
Yep. All right, SI unit. What is an SI unit? Please, somebody. What if
I know it.
SI unit?
I know it.
The S and the I are actually flipped from what you would think it would be. International
Science.
No.
Studies.
standard, guys. We have standardized units.
Wait,
When we're dealing internationally, we try to use standardized units. That's why, even though we're Americans, we use the metric system as much as we can when we're talking about science, so we can understand each other if we're a scientist in the U.S. dealing with a scientist in Europe or wherever the heck else. Okay. The SI unit for charge is the Coulomb, and it gives us a value there. How many electrons would make up a Coulomb? It'd be the number of, 1 amp times 1 second, right? It'd be the total flow of electrons. That's the number of electrons. Look how big that number is. That's a lot of electrons, you guys. 1 Coulomb is a lot of electrons. The charge of a single, or on a single electron, is much smaller. Okay, the charge. And we actually, I want you to put that in your notes. The charge on a single electron is known as the elementary charge. And it's that 1.6 times 10 to the negative 19 coulombs. You guys know shorthand? Like, you don't have to write every word out full length. You can shorten some things. You can leave certain words out, and you'd still be able to understand what you wrote. You guys should start practicing that.
What is the elementary charge? What's the elementary charge?
It's the charge on a single electron. The charge on a proton is the same, but opposite. Electrons and protons have the same charge magnitude, but they have a different symbol. Because electrons are negative and protons are positive. So they're equal and opposite. When the charges are measured in coulombs, the distance is going to be in meters, the force in newtons, and the constant K is in Newton times meter squared divided by Coulomb squared.
That's the constant.
You don't need to think terribly about it. Okay?
Do we need to write that?
You do not, because the constant is going to be given to you. I don't need you to memorize it, guys. This is intro to physics. Okay? It's not physics. It's not AP physics. When we're about to watch this video, remember this guy teaches high-level high school and entry-level college courses. Yes.
You point out.
No. You know why I don't have whiteout?
Should be using pen.
Because I never make mistakes. No, because I use a whiteboard and I go. All right, here we go. The electric force, like all forces, guys, electric force, like all forces, is a vector quantity. Do you guys remember the supervillain from Despicable Me?
Yes.
What was his name?
The blind guy.
His name was Victor, but his
Vector.
villain name was
Vector.
Oh,
Vector.
yeah.
Vector because he was into this whole magnitude and direction. If two charges being considered are both positive or both negative, the sign of electrical force is positive and the force is repulsive because they're the same charge, same type of charge. If the two charges are opposite in sign, the force will have a negative sign and the force is attractive. All right, cool. We knew that already. Video time.
So
I
what
gotta
is
start
that?
over.
You basically have a
Here we go.
Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 4. It's on Coulomb's law, which is a physics law, but also has huge ramifications when it comes to chemistry. And so if we look at a simple atom, this right here is heat.
Oh, no!
What an atom
Oh, I
actually
didn't
looks
catch
like.
it in
Using
time.
the gap, it's Coulomb.
Did you guys hear what he said?
Nope.
It's law, which
Okay. Shh. Some of you probably heard it. Give everybody a chance. So he does have a model of an atom here. This atom has 2 protons, 2 neutrons, and 2 electrons. So it is not an ion. And it is the most basic of the isotopes for this particular atom. It's not special at all. Everybody know what it is?
Wait, there's 2 electrons.
What subatomic particle, the number of, determines the identity of the atom?
Helium.
Guys, what
Oh, that is
subatomic particle,
Protons.
which subatomic particle, the number of that subatomic particle gives the identity of the atom?
Protons.
Protons. How many protons?
2.
That is the atomic
Number.
number. Okay? Atomic number, look at your periodic table.
Helium.
It's helium.
Oh my goodness.
All right, cool.
which is a physics law, but also has huge ramifications when it comes to chemistry. And so if we look at a simple atom, this right here is helium. It's going to have 2 protons, 2 neutrons, and 2 electrons. What's holding those electrons around that nucleus is going to be Coulomb's law. And so if we were to look at the chart.
Okay. Ah, got it. I didn't quite get that before we put the arrows up. So we've got these electrons. Has anybody ever played with a pinball machine?
Yeah.
They got little buttons and it triggers little paddles inside and the balls go. Beep, 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 beep.
Yeah.
The electrons, some people get it wrong. It's pretty common because you see the model of electrons, like a Bohr model, and well, they're in rings. Those are like orbits. We even use the term orbit sometimes. So if you're not careful, you might start to think that electrons orbit in a nice orderly path around the nucleus. But they don't. The rings, the orbits, just signify energy levels, how much energy those electrons have. Okay? They're pinging around the nucleus. Ping, 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 ping. You can't even determine the location of an electron at any given time. They could be anywhere. That's how fast they're moving. Okay? The only thing keeping them from flying away has to be some sort of attractive force. Protons are what charge?
Negative. Oh, no, neutral.
Literally, look at the picture. The protons are in red. Protons are positive. Electrons are
Negative.
Negative.
opposites
Attract.
We have an attractive force. That's the only thing holding on to those electrons. Otherwise, they fling away. Okay. In the nucleus, the neutrons and the protons have something called the strong nuclear force. That's in your notes, isn't it? Should be. Okay. That's the only thing holding the nucleus together, because without that strong nuclear force, what would happen?
They would fall apart.
They would fly apart. Why would the nucleus fly apart?
Because
There's nothing
it
holding
wouldn't be attracted together.
Guys, likes do what?
Attract.
Repel.
We need to, like, you guys ever heard of like thinking before you speak? You should try that, okay? Just try it, all right? You want to be the first to answer so much that you just throw an answer out. Doesn't even make any sense, okay? Opposites attract, likes repel. What's in the nucleus that has a charge?
Proton.
Only the protons. So if you've got protons packed close to each other, what are they trying to do? Trying to get away from each other. The only thing holding them together is a different attractive force, and that's the strong nuclear force. Okay, we talked about that before. That's why you have to have a certain number of neutrons in a nucleus to counteract that repulsive force of the protons between themselves. That's why you have things like beta decay, right? Okay. So we've got attractive force holding it together. I'll let him do the talking for a little while.
Charges, the positive protons are going to have a positive charge, and the negative electrons are going to have a negative charge, and those opposites attract. That's Coulomb's law. And so that's the first thing that he discovered. If we have opposite charges, there's going to be an attraction between the two. Now, the other thing he learned is that you have two like charges. They're going to repel each other. And so those two protons don't want to be next to each other. They're going to be really unstable, and the neutrons and the strong nuclear force actually hold them together.
Now, do you remember the size of the arrows? How short the arrows were? Look at the length of the arrows there. Remember, the length of the arrow shows the strength of the force. So the longer the arrows, the stronger the electrical force. The force between those protons is so much more because they're closer together. The arrows showing the force between the electrons and the protons were shorter because the force was weaker because they're further apart. Does that make sense? The closer you get charged particles together, the stronger the force between them will be. If you separate them out more, the force between them gets weaker. Does that make sense? By the way, it's the same principle as with gravity. Remember, gravity also had an inverse relationship with distance. So the further away two gravitational bodies got, the less the gravitational force would be between them. Okay, so very similar.
And did you see what happened to the arrows? The arrows got larger when we looked at the protons. And that's because, according to Coulomb's law, as those charges get closer and closer and closer, then the forces get larger and larger and larger. And so it's sometimes referred to as the inverse square rule. And so let's get to Coulomb's law. And why is it important? Well, again, it shows us that positive and negative attract. And it also tells us that if we have two like charges, they're going to repel. But the closer they get, the bigger that charge is going to be. And so Coulomb's law tells us the force between charged particles is proportional to their charges. So all you do is just multiply the two charges, and that's going to give you the magnitude. It also tells us that it's inversely proportional to the square of their radius. In other words, how far they are apart. So if things are far apart, it's going to be less charge. As they get closer and closer and closer, that charge is going to get greater.
He's misspeaking there, actually, which is rare for him. He's pretty good. He's saying the charge will get larger as they're closer together, and the charge will get smaller as they get further apart. No, the charge stays the same, but the force gets weaker as you get further apart, and the force gets stronger as it gets closer together. The charges stay the same, okay? I don't want to let that lock in with you. Our formula. Now, he leaves out the constant, and that's fine, but you've got the magnitude of the charges, Q1, Q2, multiplied by each other, okay? You'd also multiply it by the constant, and then you divide it by the radius squared, or the distance squared, okay? And it's an inverse proportion, so that's why you have that in the denominator of your problem there. That's why you're not also multiplying that onto it. You have to divide that out because it's inversely proportional.
It's very similar to the gravitational, Newton's law of universal gravitation. This just deals on the small level with charges. Now, in chemistry, it's important because we can use Coulomb's law to predict ionization energy. Ionization energy is the amount of energy it's required to create an ion. And so what's an ion? It's when you're either losing or gaining an electron.
All right. Ionization energy, the energy required to take an electron away, to strip an electron off of an atom. That's ionization energy. You are losing a negative charged particle. Now earlier, I put this together to try to simplify, and I've decided that's probably not a good idea, because then later you'll have to unlearn what I taught you because it's too simple. These are two different terms. The amount of energy is the same. That's why I thought it'd be innocent enough to combine them, but I've decided not to. Okay? So ionization energy is the energy to take an electron away from an atom. The electron affinity describes the amount of energy to add an electron to an atom. In either case, you will create an ion. Now what I want to do is show you a periodic table. And you have one. If you prefer to look at yours, that's fine too. Where is it? Should be right. You guys remember the alkali metals?
Yeah.
The alkali metals, this whole family, that vertical column, they all need what?
So for the ionization energy,
Yeah.
it's energy required to take an electron away from an atom, right?
Yes.
Okay.
Yes. And the electron affinity is the same amount of energy, but you're adding an electron.
Adding it to an electron to an atom.
Yep. Yep. So the ionization energy would be for the alkali metals, because you're going to take one away to make them an ion, specifically so that it would have the same electron configuration as a noble gas. We talked about this, if you remember. Do you guys remember? Kind of, sort of? Maybe? Ringing any bells? Ding, ding?
A little bit.
Literally just a couple weeks ago. Okay? So alkali metals, this whole vertical column, if you take one electron away, they now have the same electron configuration as a noble gas. Well, which one? Does anybody remember? Sodium, for example. If I take an electron away from that, what will its electron configuration now look like? Just back up one atomic number.
Which one are we talking about? Number? Which one are we
No, I'm looking for the daggone element, okay? It's a noble gas configuration now. If you start with sodium and you take away an electron, it's going to look, at least this electron configuration is going to look just like neon.
Neon.
Okay? If I started with rubidium and I took an electron away, it's going to have the same electron configuration as
What'd you say? What'd you say?
rubidium,
I don't know where that is. That's a big number.
Rb. We're talking about the alkali metals.
Oh.
The first column.
Wait, krypton.
No, rubidium.
Krypton.
So what would the electron configuration look like?
Krypton.
Okay, you were ahead of me.
Oh.
So good. Now, on the other side of the periodic table, we have the halogens right next to the noble gases. Electron affinity, they have an affinity for one more electron. They want one more electron. Why? So they can look like they have the same clothes on as the nobles, right? They'll have the same electron configuration as the noble gases. They'll become more stable if they have one more electron. So it would only take one more. It would only take one less. They're so close, we say they have a low ionization energy, or for this one, you'd say, I guess it has a low energy for electron affinity. I still don't like the language of that. I must not be saying it right. Okay? But does that make sense? It doesn't take much to go just one. If you're one more in, oxygen down through that whole family there, you'd need two more electrons to be like a noble gas. If we were in the alkali earth metals over here, you'd have to take 2 away. So it would take more energy to make them like a noble gas. Okay? Higher ionization energy. Make sense?
Wait, what were the green elements called? Like,
The greens are the halogens on that one. Remember that periodic tables are colored differently depending on what they're trying to discuss or highlight. Okay? All right, let me go back to video.
And so ionization is the energy required to remove an electron. And in chemistry, in science, we can actually measure ionization energy using something called photoelectron spectroscopy, or PES. Now that seems confusing, but it's actually a really simple concept and has huge implications.
You don't need to put that in your notes, but just listen.
Comes to understanding what an atom actually looks like. So we can use the data to predict the shell structure. So how do we know that we have these shells and orbitals? A lot of that is predicted through Coulomb's law, but it's also verified through PES. So who was Coulomb? He was a French physicist, and what he was doing was studying charges. A lot of people thought there was some law that was could be applied to charges, and he was the first one to really quantify that. So essentially, if we have 2 like charges, they repel. And if we have 2 unlike charges, there's going to be an attraction. And here's the equation right here. You have a Coulomb's coefficient, and then we're going to have multiplying the charges, and then we're going to take the radius squared. Now, how did he discover this before we had electronics and even electricity had really been discovered? He used something called a torsion balance, and this is one of his sketches of a torsion balance. It looks a little complex, but it's really simple. All he would do is he would take a sphere and he would charge that sphere. And so we're talking about static electrical energy. And so that was...
So what's going to happen between these 2, do you think?
they're gonna repel.
It's going to repel. They're going to push because they're like charges. So this is going to twist around the center of rotation.
Suspended by a fiber that went all the way down here in the torsion balance. So he'd give this a positive charge, and he would give this a positive charge as well. And so if we have 2 like charges, what's going to happen when I bring this one, we can see it right here, as I bring this closer, what's it going to do? You can see that it's going to push it away. It's going to repel. And so it would twist this fiber, and he could measure it. You can kind of see the scale on the side. He could measure how far it went. He would then move it away, and he would touch this sphere to another sphere that didn't have a charge. And what it would do is it would transfer half of its charge to that uncharged sphere. He would then bring it back again, and it wouldn't move as far. And so he was able to quantify Coulomb's law using a not super sophisticated torsion balance. And so why is this important in chemistry? We can use it to measure ionization energy. And so what's ionization energy again? It's the amount of energy required to remove an electron. And so think of it as just a little hand that has to come in and grab this electron and pull it off. So that's the ionization energy. And so it's going to depend on Coulomb's law how big that ionization energy is going to be, because that proton wants to hold it in place. And so let's say we were to look at something that's a little larger. So this is lithium. And so lithium is going to have this outer electron out here.
And do you see the shorter arrow?
Yeah.
So the strength of that field is weaker than the one that's closer in. So guys, the nucleus is going to be able to hold on more strongly to the electrons closer in than they can to the electrons that are further out. Does that make sense? Yeah.
Does lithium have 3 electrons?
Yes. Unless it's been ionized, and then it would just have 2. Because it would look like neon. Make sense?
Yeah.
Yeah.
Since the distance is greater, in other words, that radius is larger, you're going to require a smaller amount of ionization energy. And so that Nobel Prize was awarded to Albert Einstein for his discovery of the photoelectric effect. And what that means is if you hit metal with photons or hit metal with light, what it'll do is it'll eject these electrons, and we call those photoelectrons. So hold on to that idea. It's going to become really important in just a second. But let's build an atom for a second. And this is a simulation from PHET. What you can do, you could go to the website right down here. What you can do is you can just start dragging things in, and then it'll actually build that atom for you. So let's do that. So let's say I drag a proton in. I've now created hydrogen. You can see see on the periodic table, that's going to be H. It's got one atomic number. But let me just throw an electron in there, and where does it go? It goes right there. What's holding it in place is going to be Coulomb's law. They're opposite in charge, so they're going to be held together. Well, what happens if I throw another proton in? Now we've got helium, but look how unstable it is. Why is it so unstable? It's because those are like charges, and so they want to repel each other. Luckily, and it would never exist like that. Luckily, if we add some neutrons to it, then we can stabilize it, and so that's not going to decay. Now let's add another electron. It's going to sit in this shell, and so we've got 2 electrons in this first shell. Let's make it from helium. Let's move up, make it a little bit of unstable lithium. We'll stabilize that with a neutron. Now let's add another electron. What happens? Well, it sits right there.
Molten, we can look up family members later.
In other words, it's in the outer shell. This is in the outer shell, and this is in the outer shell. So why is it that those first 2 electrons are going to be on the inside shell, and the outer electrons are going to carry, or excuse me, those additional electrons that we add are all going to be thrown to the outside? That has to do with quantum mechanics and quantum physics, and so it's quantum numbers that are determining that. But how did physicists figure this out? How did chemists figure out that there's going to be a 2 in the first, and then we're going to have 8 in the next, and we're going to have all these orbitals? Well, we owe it to the photoelectric effect. And so going back to that again, that's Einstein's theory that if you hit matter with light, it's going to eject these photoelectrons. And so let me show you photoelectrons.
I won't go on further with this because it's way beyond what we need for this class. So we're going to head back to our lesson now. If you want to watch the rest of that, by all means, please do. All right, examples. We're going to start using this formula. All right? I think you have the basic principles. I hope. If not, you're going to have to look back in there, read it again, especially if you were on other websites, not paying attention. Okay? Let's run through this. If you don't have a calculator, what do you need?
A cow.
You need to get a calculator. I've got some on the wall over there. So, this example, we've got 2 objects. They call them object A, object B. And they're both positively charged. And we're given both of those charges. We're also given the distance between them. It's asking what's the force, what's the electric force on object A. By the way, it'd be the same force that would be on object B, right? Because they're pushing on each other. Newton's third law of motion, equal and opposite, right? So, we first of all plug in all of our numbers into our formula. They've done that for us. We're just confirming that we know how to get it in our calculator, right?